And this bottle is one of the most dangerous things I'll ever work with. It fumes in open air, it explodes the moment it touches water, and it will dissolve almost anything it lands on. This is sulfuric acid, and I want to show you why it's so dangerous. I couldn't think of anything better than using a raw chicken drumstick. Skin, muscle, bones and a little fat. Honestly, not that different from me. As soon as it touches the surface, it starts to bubble. The tissue boils and shrinks, and it's literally breaking apart, and even turning into this carbon black sludge. And that's from several drops. So yeah, this acid will do that to pretty much anything organic. Now, technically, I'm organic too, which means this acid would do the exact same thing to me. So everything about handling it comes down to one rule: it does not touch skin. That's why I'm wearing gloves, and a couple more on top of that. It probably looks paranoid. It isn't, because watch what happens when I put just a few drops on a normal latex glove. It turns black almost instantly, then starts to wrinkle and fall apart into this strange, melting polymer-like mass. And if this stuff spills, you can't just grab a sponge, because it will dissolve the sponge too.
So at this point, you're probably wondering, what does this have to do with shampoo? And even more strangely, marshmallows.
Many of the products around your home are connected by one group of chemicals called surfactants, and they are literally everywhere. But we are interested in exactly one of them, one molecule that was once in almost every shampoo on Earth. SOS, sodium lauryl sulfate. If you go to your bathroom right now and check the ingredients on your bottles, you'll probably find a slightly different one, sodium laureth sulfate, not lauryl sulfate. It's basically the same molecule, just with an extra toxic group on it. Scientists found that laureth sulfate is gentler and less harsh on the skin, so these days it's used more and more in personal care products. You might even see a label that says sulfate-free, which just means it contains other, milder alternatives, something that's become very popular in recent years. Anyway, the reason a surfactant is needed in shampoo comes down to a few things. It foams, it mixes together things that normally refuse to mix, like oil and water, and it cleans. And I need to say this, regular soap is also surfactant, and basically the first one ever made.
Okay, but what about marshmallows? What does that have to do with it? Well, a marshmallow is basically solid foam, and SOS helps keep it fluffy and stable. It's FDA approved in the USA, but interestingly, it's banned for use in food in Europe. Personally, I would not eat it.
SOS was first made back in 1930s as an industrial detergent. It became especially important during World War II, where it was used in aggressive cleaners that scrapped down military equipment. Then, in 1950s, it spread into everyday products. And the strangest part of all is that it ended up in toothpaste. If we look at the structure of SOS, it's made of two parts, a long chain of carbon and a sulfate group, sitting right on the end. And that sulfate group, it looks suspiciously similar to a piece of our superacid. And that is not a coincidence. SOS is made by taking a long-chain alcohol and sulfonating it. And the alcohol it starts from, it has a surprisingly harmless origin. It comes from coconut and palm oil, oils that are rich in something called lauric acid, which is what most of the world's lauryl alcohol is actually made from. So this is the alcohol I needed to make SOS. And right away, there is something strange about it. It's completely solid, but it looks like it was poured into this bottle as a liquid. So what's going on here? The answer is, its melting point, which is only about 24 degrees. That's barely about room temperature, and right now, my lab is just cold enough to keep it frozen. And keep that number in mind, 24, because it was about to cause me problems for the rest of this video. But before any of that, I needed to melt it down so I could wait it out. I dropped the bottle into a hot water bath and set up the rest of my glassware. Once it was liquid, I weighed it out about 80 grams, took it to the fume hood and poured it into the flask. Then I measured out about 30 milliliters of this terrifying liquid. I poured it into the dropping funnel and got everything ready for the reaction. So I started adding acid to the alcohol, and almost immediately, the temperature started climbing. By around 40 degrees, I needed to start cooling it down. And maybe you're already wondering, why didn't I just cool it from the very beginning? Here is why. The alcohol freezes below 24 degrees, so if I cool it too early, the whole mixture would freeze. So basically, I had to keep this thing trapped in a tiny temperature window for the next hour, not too hot and not too cold. And the whole time, the reaction was fizzing, because it was releasing hydrogen chloride gas, which you could actually see coming off the liquid. And HCl is seriously corrosive, so I had a scrubber full of sodium hydroxide solution running the whole time. Then a solid started forming in the flask, and at first, I thought this was some kind of inorganic salt crashing out. Then I checked the thermometer, and 20 degrees. It was just the alcohol or the product freezing. So I took the ice bath away, hit it with a heat gun, and a few minutes later it had melted. And from there, it turned into this ridiculous loop. Add acid, it freezes, melted. And even after the very last drop of acid was in and I left it to stir, it froze one more time. So I melted it one more time. And then, when it finally settled into a stable liquid, I took a proper look at it. And right away, I knew it was a problem, because it had turned brown. And brown is basically a warning sign. It meant that mixture was full of junk, so there was no way I was putting this in my head looking like that. So I grabbed a big beaker and poured it all in, and at this point the solution was extremely acidic, which made sense, since I just treated it with a superacid. But what actually happened inside that flask? Basically, a sulfate group attached itself to the alcohol, which was exactly what I wanted, and a molecule of HCl formed in the process. Some of that hydrogen chloride escaped as a gas into the scrubber, and the rest stayed dissolved in the solution. But here's the catch, this still wasn't SOS. What I had was the acid form of it, to turn into the actual sodium salt I wanted, and neutralize all the leftover acid at the same time. I needed to add a base, so I added an excess, about 2 equivalents of 10% sodium hydroxide solution. Since a strongly basic environment keeps SOS safe, the color shifted from brown to yellow. Now the whole solution was loaded with inorganic salt, table salt from the neutralized acid, plus extra base. I poured in 500 ml of acetone. The junk sank to the bottom, and my product floated up in the acetone on top. And then I look at it, and something was very wrong. SOS is almost completely insoluble in acetone, so if my product was really in there, this solution should have been cloudy. There should have been solid floating around in it, and instead, it was perfectly clear. So there I was, staring at this flask with one question. Did I actually make any SOS at all? There was only one way to find out, so I started adding more acetone. And then, finally, a faint white solid appeared, drifting down through the liquid. Alright, next step. And you can probably guess what's coming. Filtration. So I set up a vacuum filter on a 2-liter flask and started pulling the solution through. Look at the filtrate. The product started crashing out there too. You can't even imagine how annoyed I was. I dumped the whole thing back into the beaker, added more solvent, threw it into the fridge, and walked away for the night. The next morning, there was a yellow solution, with a batch of crystals sitting at the bottom. So I filtered it again, and this time, nothing crashed out in the flask below. It ran through perfectly, leaving white crystals on the filter and clear yellow solution underneath. Then I swabbed the flask and washed the crystals few times with fresh acetone to rinse out any leftover impurities. After the washes, I dried the crystals for half an hour. And it looked great, soft, fluffy, white powder. But it still smelled strongly of acetone, so it wasn't done yet. 1 hour on a hot plate at 60 degrees, then into a flask with an adapter and a vacuum hose, and 1 more hour of heat under low pressure to pull out the very last of the solvent. 25.1 grams, a yield of about 20%, which, let's be honest, was bad. Most of my product was still trapped in that yellow solution, and a chunk of it had washed away during that rinses. But here's the thing, I was never chasing a big number. All I ever wanted was a small amount, pure and clean. So I take a clean beaker and pour in the water, and then I add the SOS and stir until it dissolves. And this takes a little time. It even needs a bit of heat before the SLS will fully go in.
As you can see, this simple mixture of water and SLS is very runny, and it doesn't really look like a shampoo yet. So, how do we make it thick?
I add a mystery white powder, but not dry, as a solution dissolved in a little water. And watch, the moment it goes in, the whole mixture starts to thicken until it has that exact familiar shampoo texture. Now, if you're thinking this powder must be some special thickener, it isn't. It's just regular table salt. This process even has a name, salt thickening, or more scientifically, micelle transition. The salt makes those molecules link up into long, tangled chains, basically microscopic spaghetti, and all the tangling is what makes it thick. Next, I add a little glycerin. It pulls moisture into the skin and stops everything from drying out. And now we are almost done. Almost, because there is one last problem. When I measure the pH of the solution, it comes out pretty alkaline, which isn't surprising. Surfactant solutions tend to sit on the alkaline side. But our skin, and especially our scalp, is naturally a little acidic. So to bring the pH back down, I add citric acid. I just keep adding it slowly, until the whole thing settles into a neutral or slightly acidic range.
And that's it. The shampoo is done. It's the most basic shampoo you can make, and honestly, washing your hair with dishwashing liquid would probably still be better. But considering that I wash myself with something called 1 in 10, I will not notice much of a difference here.
I transfer it to this clear bottle, and of course, put a label on it.
The shampoo is ready, and it's time to test it. I know you have a question, where am I gonna wash my hair? And honestly, doing this somewhere in the shower felt kinda boring, so I'm doing this here, in the lab. We have this nice sink, and this super tall faucet. And actually I can use this emergency eye wash station. It looks like a shower head. Yeah, honestly, whatever. Let's just do this. Alright, my hair is wet, and now comes the moment you've been waiting for. Yes, you've been waiting for, not me. I even printed out the photo of my hair, just in case I need to remember how it used to look like. 3, 2, 1. Oh no. Okay, so far so good. No burning, no weird feeling, but there is one thing. This stuff smells kind of bad. And I really hope that's not my hair starting to decompose. At least, it's foaming. And if this stuff foams on my head, that means one thing, it's shampoo. I can confidently say that we synthesized shampoo from SUPERACID. And now, let's wash off this stuff as fast as possible. Okay, I hope you enjoyed this video. Don't forget to subscribe, like, support on Patreon, and see you in the next video.